Good afternoon. So it's my pleasure to introduce today's colloquium speaker. So let's welcome Jean-Michel Léger. He is with CEA-Leti. And sorry, so my French is not existing, so I have to explain the abbreviations in English. So CEA stands for Commission on Atomic and Alternative Energies, I guess, if this is right. And Leti is a laboratory for electronics and information technology. And in order to keep the dimensions right, so this laboratory is 1,800 people, mostly in Grenoble. And so Jean-Michel holds a PhD in physics, and already with his PhD, he started to work on helium magnetometers, so optically pumped magnetometers based on helium. So the first big mission is your group at SLT, which deals with magnetometer developments, but not only. So of course, there's all other stuff ongoing in your group. So the first big mission was Swarm. So we have it here in the title, which is the 3-satellite ESA mission for the Earth field observation. And luckily, of course, we meet each other in space every couple of weeks. So we get very close between his scalar magnetometers and ours, which is on the Macau Science satellite mission. We get close as 20 kilometers. And fortunately, so our readings match up quite well. So, but of course, you not only deal with the Swarm mission, so that the next big activity, which is now ongoing, is NanoMagSat, which is an interesting CubeSat follow-on mission from Swarm in a reduced compact size, but same or even improved quality. So there's a lot to be heard today. Thanks for coming again, and please, the floor is yours.
Thanks for the introduction, Leonard. Sorry. Okay, yeah. So I will indeed present you some results from Swarm to NanoMagSat and helium optically pumped magnetometers for Earth observation. Let's first have a look at the motivation for the Earth field mapping. It started pretty early on with practical applications like navigation and attitude determination, more recently with ore deposit characterization, and even more recently with preventive actions against magnetic storm consequences like power grid management or satellites operation. And also, of course, since the 1980s, we have some space missions that are dedicated to scientific issues. So first, the characterization of the core field of the Earth, and then its evolutions, like the secular variation or the North Pole drift. We can also monitor the currents, oceanic currents, by averaging over a long period of time. And we might also get some information about the temperature or the salinity of the oceans thanks to magnetic measurements. Last but not least, there are now a lot of space weather activities studying the interaction between the solar wind and the magnetosphere. So monitoring the Earth's magnetic field started, of course, from ground, and it was, well, the first compass we have some trace of. It dates back more than 2,000 years. And the Carta Pisana, you can see, was issued by the early 13th century for navigation charts. That's a map of the Eastern Mediterranean Sea for navigations at the time. And the last picture is an illustration of the La Pérouse expedition by the late 18th century, which also carried a lot of scientific instruments. Now it has been complemented by ground observatories that are permanently monitoring the magnetic field. You are here, the red dots illustrate the intermagnet network of ground observatories as of 2010, I think. And the first magnetic observatories in Great Britain and France started in the 16th century. It has been complemented in the second half of the 20th century by airborne surveys, either by helicopter or plane. mostly to characterize ore deposits. And the magnetometers have been flown as early as 1958 on Sputnik 3. So it was basically one of the very first scientific payloads on board of a satellite. Between 1964 and 1978, only scalar magnetometers were flown. And the scalar information alone does not help you to build a complete field model. You need also to have either a perfect knowledge of the equator or to get some vector information in complement to complement the scalar ones. The first high-resolution vector measurements were carried out from space, were carried out during the Magsat mission. It was a US mission that lasted, unfortunately, only for 6 months, but already demonstrated the benefit of using both scalar and vector magnetometers simultaneously. Then we had to wait about 20 years before a new high-resolution mission dedicated to the Earth field mapping was launched, and it was the ÖAW satellite launch in 1999, which was followed closely by CHAMP, SAC-C, and we then had to wait again for slightly more than 10 years for the Swarm launch, which was a constellation of 3 satellites, actually. The first missions were operating ÖAW and CHAMP. We operated over other magnetometers delivered by Leti, and then we switched to optically pumped magnetometers with Swarm. So the challenges for the low Earth orbit magnetic missions, you have different sources, like the inner ones, the core source, the lithosphere, plus the interaction between the solar wind and the magnetosphere and the ionosphere. Of course, satellites offer a much improved geographical coverage with respect to the ground observatories, which are quite sparse and uneven distributed. So you have none basically in the oceans, not many in the southern hemisphere. You can get a complete global coverage thanks to quasi-polar orbit satellites. But now the point is you have also to separate the different magnetic field sources. And like, for instance, and the order of magnitude of these sources at, let's say, 500 kilometers altitude is very different. The core field is between 20 to 60, 65 microtesla, and it dominates much weaker signals. Like, for instance, if you want to look at the oceanic tides signals, it's of the order of 1 nanotesla. So you have to get rid of that. In addition to that, some of the phenomena you are looking at are related to the geographical position, whereas other signals are correlated with the local hour at the satellite position. So in order to be able to average, in order to get the very low signals, the weaker signals, you need to have an absolute measurement that is below 0.2 nanotesla. Basically, if you want to recover properly, for instance, the oceanic tides, you will have to measure for a long time. Same for the secular variation. You want to make sure that the magnetometer has not drifted during the period of operation. So basically, that's the main requirement on the scalar magnetometer. On the other thing of the vector measurements, you must know the attitude of the satellite and of the vector instrument. And basically, with an orientation knowledge which is of the order of 5 arcseconds, which is not much. It's slightly more than 1 millidegree. So typically, here illustrated by the case of Swarm, the LEO satellites have a typical magnetic payload combining vector magnetometer and scalar magnetometers. In the case of Swarm, the scalar magnetometer was an ASM sensor, and it really intended to provide the absolute scalar data, the key parameter being the accuracy, and the objective is really to calibrate the long-term drifts of the vector magnetometer. And on the other end, and it's very similar to the role that was played by the coupled dark magnetometers that have been developed by your institute for the CSCS-1 and Magsat satellites. The VFM magnetometers can be seen as variometers because they are subjected to drift. They will deliver the vector measurements, and the key parameter for them is really the resolution. Of course, you want to have a pretty good stability because you don't want to calibrate permanently to carry out permanently a scalar calibration, but nevertheless, you really focus on the resolution of the sensors. And they are always coupled to a star tracker on a very stable optical bench that you can retrieve the actual attitude of the measurements you carry out and transfer it to the next reference frame. So if we now go to the Swarm Absolute Scalar Magnetometer, it's a very classical magnetometer, an helium optically pumped instrument, which is basically a field to frequency converter. So you have here a scheme of the different levels that are involved. We operated on the metastable state, that is, we are first to populate some atoms, about 1 out of 1 per million atoms from the ground state to the metastable state. Then we proceed to selective optical pumping with a laser, typically on the D0 line. The net result of that cycle is the polarization or the alignment of the metastable state sublevels here. And you can then proceed to the magnetic resonance between adjacent sublevels. The laser will therefore have a pretty key role in the sense that it will first provide the signal amplification through the optical pumping cycle, and it will also provide the resonance detection. So that's the way you are going to really measure the magnetic field, because the transparency of the cell varies when you go through the resonance. Now, whenever you are talking about scalar magnetometers, they are usually prone to dead zones. That is, depending on the actual attitude between the satellite and between the instrument, and the magnetic field, you can indeed amplify the resonance signal or not. And clearly, whenever you are talking about a mobile application, it's a problem. So we came up with the specific architecture where the magnetometer isotropy is achieved by controlling the RF field direction, which has to be perpendicular to the scalar magnetic field, and the laser polarization directions. We are using linearly polarized light because it's very easy to control the direction of the polarization in the polarization plane, whereas if you are using circularly polarized light, what counts is really the direction of propagation of the light, and therefore you have to move the complete sensor, which is not so straightforward. So we have here a scheme where we can achieve exactly the same pumping conditions for the atom, whatever the direction of the magnetic field is. In addition to that, we have the choice of linear polarization also helps us to have no light shift effects. In fact, we have light shifts, but it does not translate into modifications of the resonance frequencies that is observed at the magnetometer level, because basically CM+1 and M-1 are shifted by the same amount, and so that these two transitions are shifted also by the same amount, but in the opposite directions, and the overall resonance line center is not affected. So that makes it very insensitive to slight drift of the laser wavelengths, which is always a challenge also. Now, that was the baseline was really to deliver scalar measurements, but we also proposed an experimental mode in which we could derive simultaneously the scalar data plus vector measurements. The way it's carried out is by applying 3 AC signals, excitation signals, to the helium cell at the 3 given frequencies, and then looking into the scalar measurement, you can demonstrate pretty easily that you will see some components which are proportional to the projection of the magnetic field along that direction. So by just demodulating the scalar output at the 3 frequencies you have applied to the sensor, you can get information about the component of the magnetic field along that direction. The advantages of that configuration is first that you have no offsets, so you only have 6 unknown parameters to determine. That is basically the Swiss transfer functions, linking the amplitude of the signal you see at one given frequency and the component of the magnetic field along that direction, plus the deviation from orthogonality between the 3 directions, which is pretty stable actually. So you have to characterize it once, mostly on ground, and then it doesn't change over the complete duration of the mission. It's an open loop design, so there is no feedback. It's pretty simple, actually. The second point is that you've got collocated synchronous scalar and vector measurements. That is, the same atoms sense both the scalar and the vector measurements. So you are no longer affected by spatial gradients whenever you want to carry out the scalar calibration. And that's really a very good advantage because any perturbation field from the satellite won't affect the calibration of your vector mode. Now, actually, the resolution, the vector resolution is not constant. What is constant is the attitude resolution, which is of the order, again, of 3 to 4 arc seconds. So basically, let's say 1 millidegree. And the vector resolution depends upon the modulus of the magnetic field. So you will achieve a much better vector resolution at low fields than you will achieve at high fields. And last but not least, you get also a quality index for the vector data because you can compute the scalar magnetic field from the 3 components, and you have the direct comparison to the DC measurement of the magnetic field, which is delivered by the scalar instrument. Of course, there are a few operating constraints. The first one is that you must really make sure that the modulation frequency are chosen, such as there is no spectrum overlaps. Because, of course, if you have some influence from one frequency to the next, you will interpret it falsely as a component, as a bias in the component measurement. The transfer function stability determines the vector accuracy, but you are in open loop, so it's really basically a matter of the CTE of the sensor. In this case, it was peak, so it was not that good. It was 47 ppm per degree. We have replaced it by alumina, which is almost 1 order of magnitude better than that for the NanoMagSat. So basically, you don't care anymore about any temperature dependence, which is also a big difference with respect to flux gate, for instance. Now, of course, also the field noise must be below the scalar resolution, because otherwise, if you have any geomagnetic signal at the modulation frequency, you are again going to falsely interpret it as a component, as part of a component along that direction. And last but not least, but I already mentioned it, the vector resolution is degraded with respect to the scalar resolution. And in the case of the helium magnetometer, the amplitude of these modulations were of the order of 15 nanotesla. So if you operate at 50 microtesla, you have a factor of 1,000 between the scalar resolution and the vector resolution. So in order to be able to vectorize the scalar measurements, you need to have a pretty good scalar resolution in order not to have a too poor vector resolution. So this was demonstrated during the node commissioning. So the vector mode was turned after a few hours, so very early on in the mission. And we demonstrated that it would deliver data that were of the same order of quantities than the standard vector magnetometer. So you have here a comparison between a Chaos 6 model, the ASM data, only based on the ASM data, plus, of course, the attitude information delivered by the star trackers, and the one from the standard VFM. And what you can see is that basically you retrieve the signals with exactly the same accuracy. And these ASM-V data have been used to construct a very high quality field model, despite the boom distortion, because the boom was not designed to guarantee the attitude transfer between the star cameras and the MAM at the tip of the boom. But it turned out it was quite stable. We had to recalibrate it every 10 days or something like that. So it was no big deal. I mean, it was very low frequency evolution, so it could be very easily filtered out. And the ASM-V data have been used to contribute to the DGRF 2015 and the IGRF 2020, and they are submitted now for DGRF 2020 and IGRF 25. So we anticipated that we would get such results, and we saw that at a very good opportunity to simplify the traditional magnetic payload combining 2 instruments. And we have now the opportunity to fuse it into only one single magnetometer. And that was the beginning of another story. I will come back later. That is the NanoMagSat mission. Now, In addition to the vector mode, we also had an ASM burst mode, the scalar mode, and it was initially developed to sense the magnetic environment because, as I mentioned, you must be sure that you have no geophysical signal at the modulation frequencies. And since we had no measurement at these frequencies with the resolution we could achieve on the scalar magnetometer, we had first to sense the environment. So we operated the scalar mode for a few orbits, I don't know, 1 or 2 days during the in-flight commissioning, and then we stopped it. We didn't look into it for months. Our partners from IPGP, nevertheless, looked back at the data, and they became aware of the fact that they could detect plasma bubbles related signals or Whistler signals that are correlated with that are produced by atmospheric lightning. And then you see a dispersion that gives you some information on the state of the ionosphere. So that's of interest for space weather application because it gives you an idea of what is below the satellite. It provides you with the means to sense the ionosphere below the satellite. And it has been used as a new product. And I think the first work on that subject was by 2017 or 2018, I don't remember exactly. We had already started with the NanoMagSat, but then, of course, the scientists came back to us and told us, okay, it would be nice also to have a much extended bandwidth for the scalar magnetometer so that we can also go further into our studies. We were limited to 100 Hertz bandwidth with the burst mode of the ASM, and we could not operate simultaneously the ASM in burst mode and in scalar mode, and in vector mode, sorry. So the first idea for NanoMagSat was taking benefits from the lessons learned by Swarm, was really to merge everything we had learned from Swarm and try to develop a new mission. Initially, with only one satellite, we started with class. They wanted to have a 6U satellite, but it soon turned out to be very challenging because we wanted to achieve the same performance for the scalar and vector modes as for Swarm, which was not exactly the same type of satellite here. Starting with a 6U, we could not manage to fit the deployable boom, for instance. So we moved slightly, quite slowly, to a 12U satellite. And then it was demonstrated in 2015. So we had started to develop the instruments and so on, demonstrate what we could achieve. And then there was a call by ESA, a scout call, asking for missions which would be carried out at pretty low cost, pretty short duration, that is basically 30 million euros, 3 years before the launch of the mission and the launch of the satellite, which is for a new instrument quite challenging. And we came up with, but given the funding, we thought we could fly 4 satellites at the beginning, then we restricted it to 3 satellites, and combining a polar satellite for the very good geographical coverage with 2 inclined 60-degree satellites so that we get a quick local hours drift, and we can also resolve the ambiguity of the polar satellites. There is some along track ambiguity. We are always flying north-south or south-north bound, and that gives rise to some ambiguity. So combining it with 60-degree satellites would help us resolve that. And then as far as the altitude is concerned, at the time, the orbiting law imposed a 25-year lifetime. It has been changed now to 5 years, which is even more challenging because you don't know exactly what the solar activity conditions are going to be. So you want to be pretty close to the sources, but the lower you are, the less, the shorter the mission. And you have to demonstrate that you won't stay too long in orbit because we have no deorbiting means. We have no fuel on board and no room for it. So basically, at the very beginning, we were aiming between 560 kilometers and 600, and this has been restricted between 560 and 575, taking some assumptions about the solar activity. So there are 2 sets of objectives for the NanoMagSat mission. The first one is the Earth magnetic field study. So it's just exactly the same as for Swarm. So you go from the core, which is really the domaining feature. Then you remove it, you go to the magnetosphere. The order of magnitude is now down to a few tenths of nanotesla. From that, you go to the ionosphere, which is even slightly less, below 20 nanotesla, I would say. Once you have removed all these effects, you can look at the crest effect, the lithospheric field, which is now below 10 nanotesla. And in the end, you can, once you have removed all these effects, you can have a look at, for instance, the ocean flow, the tides, which is of the order of 1 to 2 nanotesla at the very maximum. So specific to NanoMagSat, we want to achieve exactly at least the same resolutions than for Swarm satellites. So on 60 new satellites instead of 9 meters long and 560 kilogram satellite for Swarm, which is in itself a challenge. And we want also, thanks to the 60 degrees inclination orbits, we will have a recovery of the fast parametric changes in the core, whereas we had to wait for several months for Swarm to get the same information. The second set of objectives for NanoMagSat is really related to the ionospheric environment. So we are targeting to get some, so we have a combined payload of one magnetometer, one vector magnetometer operating at high frequencies, and a long mirror probe, MNLP, that is developed by the University of Oslo. And we will combine it with some GNSS signals, occultation signals, and so on, to get a pretty accurate image of the ionosphere, for both at the satellite altitude and below it. So the payload we started with was the Miniaturized Absolute Magnetometer. Basically, it was really an evolution of the ASM-V. The operation principles are completely changed, but we replaced two subsystems in order to open the way to a very significant miniaturization. You have here a picture of a Swarm ASM-V, and that was a prototype of the NanoMagSat Miniaturized Absolute Magnetometer. It's now even shorter than that. It's about 8 centimeters in length and less than 3 centimeters in diameter, whereas this one was more like 30 centimeters in length and 5 plus something centimeters in diameter. And for the electronics, we similarly could reduce very significantly the volume of the electronics. Now we are operating 2 magnetometers, actually, 2 optically pumped magnetometers. But replacing the fiber laser we had on Swarm by a laser diode helped us to reduce the volume of the electronics from 5 liters down to 1.3 liters approximately. We will operate simultaneously the scalar burst and the vector modes, so we will get all the information in one sensor. We don't need to switch from one mode to the next, as was the case for Swarm. We extend the scalar bandwidth to 800 Hz. And the performance has slightly improved. We will divide the scalar resolution by a factor of 2, aiming at 0.5 picotesla per square of hertz. And the vector resolution will be below 1 nanotesla per square at 50 microtesla. We hope to be able to achieve better than 0.5 nanotesla per square of hertz at 50 microtesla, which translates into 0.2 nanotesla at 1. And the accuracy, the scalar accuracy, the specification is below 50 picotesla for the duration of the mission, but we consider we can achieve 20 picotesla or even 10 picotesla on the long term. We have observed absolutely no drift on the ASM-V data, so there is no reason why we would have any on the NanoMagSat 1. And the vector accuracy is going to be better, actually, be significantly better than 1 nanotesla, but the specification is at 1 nanotesla. And here you have spectral density, so you see a lot of peaks, which are the mains and so on. But basically, you see here the resolution was of the order of 0.6 picotesla per square of hertz at the time. Now, the map vector capabilities are restricted, as I explained earlier, to low frequency. By principle, we can't go much above 1 hertz. In addition to that, whenever you are operating with a scalar magnetometer, you can only detect structures which are along the main magnetic field. Because if you think of a 50 microtesla static magnetic field, and let's say a 20 nanotesla structure that will be perpendicular to it, when you compute the modulus, you see that you have no means to detect the 20 nanotesla anymore. So that was the next point with our scientific colleagues from the IPGP. They thought, okay, it's nice, we can see a lot of things with this scalar burst mode, but we'd like to be able to see also the components that are perpendicular to the magnetic field. And then that means that you need also to have really a vector magnetometer, which is capable, plus they wanted also to know the polarization of the signals they could detect with the burst mode. And then you really need to have a vector magnetometer with an extended bandwidth. And that can be achieved by designing an helium magnetometer relying on parametric resonances instead of the classical Zeeman resonance. And well, nothing new. The principles were proposed back in the late 60s. They have already been flown, I mean, mostly for interplanetary measurements, not Earthbound satellites, but nevertheless. And we are looking, and of course, with unprecedented resolution for space measurement in those bands. Typically, a vector resolution for the flux gate is typically around 6 picotesla per square of Hertz, and we want to go down by more than 1 order of magnitude with respect to that. So we started with one magnetometer that could do the job of the traditional payload, and we are back now with 2 magnetometers. Which also explains why we have slightly expanded the size of satellite. So the high frequency magnetometer I was talking about is issued from developments that were carried out for magnetoencephalography and that have been adapted for operation in the Earth field. So the optical probing process is exactly the same as the one for the MAM instrument. We are operating the parametric resonance of these atoms in near zero field conditions, and we operate this instrument exactly the same way a flux gate is operated. That is, we compensate the local magnetic field and measure the currents that help us to compensate this field. So we are in a closed loop operation. The components for this magnetometer are very, very similar to the ones that are used for the MAM, to the point that we are going to use the same laser, for instance. So that's the reason also why we have all the electronics for the 2 magnetometers into one single DPU. It's a problem whenever you want to go for qualification because you have only one DPU and you must operate 2 magnetometers. So usually you are not under the same conditions, be it for the temperature, of course, for the field range and so on. So it's a bit tedious, but nevertheless, I mean, we had no choice also to put that into a nanosatellite. It's already very packed. So the sensor itself, you see a picture of the prototype here. It's a sphere of 5 centimeters in diameter. And here are the main features. So we have a high vector resolution combined to a high magnetometer bandwidth. Resolution is between 130 femtotesla per square of Hertz for 2 axes, and slightly degraded for the third one, so around 170. And that's within a plus minus 70 microtesla measurement range. That is, we achieved 9 decades between the resolution and the full operating range. And sampling rate will be set at 2 kilohertz, so that we get a bandwidth that is the same one as for the MAM, so at 800 hertz. And we carried out some characterization, some calibration of the vector measurements, and you see here that it was slightly below 1 nanotesla, but it was really not the aim. We just wanted to have a look at what it would look like. So the 2 instruments, if we go now to the NanoMagSat current status, in terms of programmatics, the implementation phase has started by late 2024. The PDR is scheduled for February 26th. The first satellite has to be launched by contract before the end of 27.
30 minutes.
Yeah, okay, it's perfect. I'm almost done. And the third satellite should be launched no later than third trimester of 28. In terms of development status, the first point we had to develop was a deployable boom and a very ultra-stable optical bench. They are now at TRL 5. So you see a picture of the boom installed configuration, and here completely deployed. So we have to fit into 16 new satellites, so 40 by 20 by 20. And the boom takes almost half of the volume of the satellite. Now, this boom is completely amagnetic. The optical bench is really very stable. So we have had some difficulties to achieve the goal of 3 seconds deformation of a temperature range. But we are now, I mean, it's almost demonstrated right now. We need to have star cameras, and I mentioned that we had also a Landmeer probe that will be flown, but both benefit from heritage from previous space missions, so they are considered as CATs, except for the fact that we had also to qualify deployable buffer for the star tracker, because there was no way we could accommodate fixed buffers within the allotted volume. So it was an additional challenge. This one is now also at TRL, between TRL5 and TRL6. So everything is fine with it. And as far as the magnetometers are concerned, we are manufacturing right now the EQMs. We shall have the delivery of the electronics, which will be the last component that will be available by the how do you say that, autumn next year, sorry. And we have also been in charge of the characterization of the satellite subsystem magnetic moment at our facility at Herbe, close to Grenoble. And we managed to achieve a very low remanent signature, which is significantly below 20 milliamps square meter. We hope to be in the vicinity of 5 million square meter, but we have still 2 components to characterize. So we have changed basically every component of the satellite that was proposed by the prime in order to reduce the magnetic signature. And we also built a digital twin of the satellite magnetic field calculations, and it confirms compliance to the NanoMagSat magnetic budget with really a very good margin. Basically, we think we will be able to achieve the magnetic budget after compensation without any compensation. From design, we will be below the goal. And of course, we will nevertheless try to improve that by preliminary characterization. So we think we will be able to be down to 0.1 absolute accuracy, removing all the effects, and in particular the remanent effects, because we have also some effects from the HFM onto the MAM, but this one is very well characterized. It can be reduced by a factor of more than 1,000. And we also use air coils to stabilize the aircraft. And again, measuring the current is you can very easily remove that effect. So that's the current status of the mission. And well, it has been quite exciting. We think we will achieve the goals that were set initially, that is to do better than Swarm, with a budget that is about 1/10 of the Swarm mission. And the time frame for us, well, the story started in 2014, but it really started, I mean, for the demonstration and development 2 years ago. So it's still quite challenging, in particular with deployable boom, which was completely new. I mean, there was no European boom. You have some very easy deployment booms when you just have a release mechanism, but you couldn't fit that into such a small satellite. So we had really to go for a complete different new design. And it was achieved by our colleagues from Comet Aerospace in Spain, and they have done a very good job there. And that's all for it.
Thank you very much for the very interesting talk. Open for questions.
I have tons of questions, but first, on the high frequency magnetometer, I didn't catch what is the difference between the parametric resonance versus the Zeeman resonance, and do you have a penalty of trying to measure the vector accuracy?
With the Zeeman resonance, when you go down to low fields, I mean, the resonance line in the case of helium is not so narrow. It's of the order of several hundreds of nanotesla. So there is a limit to the low field capacity you can achieve. So in our case, we would recommend not to go below 1 microtesla, for instance, for the MAM sensor. For the zero field magnetometer, on the contrary, you will operate, if you had a look at the open loop curve, it's linear range between plus or minus 200, 300 nanotesla. So it's really completely different. It's zero level crossing resonance you are looking at, whereas you are looking at the Zeeman resonance. It's completely different in principle.
It is still in the atomic levels of the...
Yes. It is still in the atomic levels, yes.
And why are they sensitive to magnetic field, this resonance? Why are they sensitive to magnetic field, these resonances?
You operate the resonance at zero, and it's a zero crossing resonance. And then with the modulations, we just vary the outer magnetic field. There is no ambient magnetic field, and we superimpose some modifications there. And that's the reason why we sweep through zero field resonance. Basically, it's just like a flux gate, but the flux gate, the range would be several tenths of microtesla. The open range, it would be even maybe some millitesla in some cases, where here we are really restricted to a few hundreds of nanoteslas.
And second question. On the ISM, you said to avoid the... but you can change the polarization. Yeah. So essentially you scan the polarization.
No, we don't scan, we lock it. Whenever we apply the resonance, you get some signals at DC, at the modulation frequency, and at twice the modulation frequency. Now, the signal at the excitation frequencies goes through zero around 90 degrees, when the angle between the polarization and the magnetic field is at 90 degrees. What you get means to lock the polarization to that 90 degrees, because 90 degrees, whatever the direction of the magnetic field is, you always have a direction within the polarization plane, which is perpendicular to the magnetic field. So we just rotate it progressively as the attitude of the magnetometer changes with respect to the magnetic field.
It's a feedback on this. So
exactly, yeah.
Thanks.
More questions?
Is the magnetometer the only science instrument on that satellite?
No, as I mentioned, there is a Langmuir probe as well. Four Langmuir probes, actually.
How did you get industry to change all the structural items to become non-magnetic?
Basically, the scout call was pretty different from what you are accustomed to. ESA was asking for science experiments that could be demonstrated at a low cost and pretty short development period. And it was really, we proposed, we have chosen the prime, actually. So we designed the mission very early on in 2014 in a collaboration between IPGP for the science part and Leti for the technological part. And then we went throughout Europe, going to startups or space companies and asking who could be able to develop a satellite for us. We have got the payload, we need the bus. And so we selected Open Cosmos in Great Britain. And we are really setting the requirements. So whenever they want, like for instance, they had the standard batteries, they had operated some in-space demonstrations, but never a scientific mission. So they gave us the batteries, we characterize them magnetically, and then explain them what they should change. They provide us with their PCBs, and we tell them, okay, if you want to reduce the magnetic signature, you will have to change these components, you will have to change the way you are routing your signals through it, and so, and each time you have to fight in order to convince them that it should be done this way. And like, for instance, when we managed to reduce the magnetic signature, which was one of the main components, we had more than of the order of 20 milliamp square meter per battery and 4 packs of it. And we managed to reduce it to almost zero. So the reaction of the industry was, now that we have no longer any magnetic signature related to the battery, can we relax somehow the requirements of the other parts? We had to fight again.
Were there any heaters involved on batteries or whatever?
No, not on batteries. There is one heater that is involved on the MAM because we are using that liquid polarization rotator, and if it's operated at low temperatures, then it's pretty slow.
What heater technology are you using for your sensor?
HF heating, just like for Swarm, and it's provided by an Italian company. At the time it was Rica, but I think they have changed the name. I don't remember the name now, but I mean, it's the same product. And it's pretty good one. I mean, they are really...
It's a heater mat you are buying?
Yes.
So Gabriel might complain he had only 2 questions.
Another one.
I have a very different question because I'm not in your field. But you mentioned this that magnetometers can be used to detect lightning. And I wonder, I mean, maybe it's also a question for Werner actually, whether in the JUICE mission there's a phase where they will orbit Jupiter, right? And I wonder, you know, they have the type of lightning is very. There's a lot of types in the Earth atmosphere already. So you have these sprites, or as you say, these whistlers, which it's very strange types. So maybe on Jupiter, it's the same, or maybe there are different types. But I mean, it was an interesting idea, maybe to collect, trying to search for lightning on Jupiter to get some statistics.
Yeah, maybe. Yeah. That's a way to sound the ionosphere in the case of the Earth, but I don't know about Jupiter.
Yeah, I'm afraid we will not be that close to Jupiter itself. So we choose. It's to try to stay away because it is just too radiation. The radiation is too strong. Yeah. To be that close for this kind of measurements.
So about this, I mean, I know it's not your instrument, but this multi-needle Langmuir probe. So the point is just to have the electron density.
Electron density plus electron temperature. There is a one sweep mode from which we can derive also the electron temperature.
So we have a sweep mode, and
we have in fact 4 booms. 3 booms will be devoted to the electron density, and 1 will be devoted to the electron temperature by sweeping.
So we are not on the same boom. We are.
No.
It's probably like just.
They are here. The booms here are actually, they are 20 centimeters, and they will be deployed separately, completely separately. I mean, on the optical bench, at the tip of the boom, we only have the star trackers on the one side and the MAM instrument on the other side.
And unrelated question, but is magnetometer are they sensitive to spacecraft charging? Do you see effect of deviation from what you measure because the bus? Not at all. It's not complicated.
So I have a question. How do the overall costs, so the system costs, scale with the size of the CubeSat? So you said you started with 6U, then of course then you had on the slide 12U, 12U. Now I guess in the end what we see here is 16.
Yeah.
What is the impact on the cost? Does this scale somehow linearly, or also the launch costs? Is it the same for 16U as for 12U?
No,
or?
the launch cost is proportional also to the size and to the weight. For the cost of the satellite itself, most of it is the NRE. That is the work that is done previous to the, I mean, relative for the design, and so the manufacturing cost is not that high. Of course, with respect to what we started with CNES, we had only 1 magnetometer. Now we have 2. We have added the Langmuir probes. We have also the GNSS for the occultation and so on. So, okay, we are still aiming for the inner field. We have the same objectives as the ones we had at the very beginning with the CNES collaboration, with the phase 0, but for the rest, it's a completely different mission. I mean, we have really significantly improved the outcome of the NanoMagSat mission. We went from 1 satellite that was designed to complement the Swarm constellation to a constellation that is completely autonomous, that will of course benefit from the Swarm satellites if they are still operational at the time of the launch of the NanoMagSat ones. And I didn't mention that, but the recurring cost is, including the launch, shall be of the order between 3 and 5 million euros. And what we intend to do once we have demonstrated that the satellites operate correctly is to extend the intermagnet the intermagnet
Ground-based network?
network, sorry, I was searching for the word, to an intermagsat network that is launching several satellites to have a permanently some satellites in orbit, and with that type of constellation that is combining inclined orbits with polar ones, so that we get both geographical coverage and the local hours.
Of course, reproducing it is then not that expensive.
Then it's not that expensive, so that should also interest some countries that will not be able to develop a completely new system, but which are interested in science behind that.
Okay, so we have Hans. One or two more questions.
Thank you. Very super exciting talk. I have one question. When you run the ASM in burst mode and you detect the plasma bubbles, what are the sources of the plasma bubbles?
Oh, okay. So that would be a question for my colleagues of IPGP. I'm sorry for that. Mostly, I didn't insist on that, but at Leti, we are really designing. We are engineers, and we are working in collaboration with IPGP, where the science teams is located. So I know that they can detect plasma bubbles. Now, what are the physics behind it? What is the origin of these plasma bubbles? I'm really not the specialist to talk about it. Sorry for that.
Okay. One more question.
Very nice talk as well. I was wondering about, you talked about ocean circulation at some point. What are the scale size of, and what do you really measure? Because you measure the...
we measure the magnetic signal, which is of the order of 1 nanotesla.
Right.
And to be able to detect it, we need to average. That is the reason why we need to have a very stable reference measurement.
For how long do you have to average?
For months or...
It's that large scale.
Yes. Basically the requirement for Swarm was that we would be able to derive the absolute accuracy better than 50 picotesla, over the duration of the mission, which was intended to be 4 years and a half. It has been now flown for 11 years, and we have demonstrated that we are significantly better than the 50 picotesla that were required.
Thank you.
You're welcome.
Okay, so before we finish, two more announcements. So there are tickets available for the dinner in the evening. So just tell me who would like to join us for dinner. It will be at 7 o'clock in the city center. And the second one, so if you have more questions, maybe for the bus or the system or magnetometers, so we will continue our discussion in the seminar room. So all are welcome to come with us for this further discussion. And with this being said, so let's applause Jean-Michel once more. Thank you very much.